facultad.
Triste.
Bueno, lo que pasa, bueno, la triste, así resumidas cuentas, es que surge de la división de lo que era la Facultad de Física. Ya sabes, las amistades, las buenas relaciones hacen que la gente se separe y surge esta de la luz y la materia.
Ajá.
Y la buena, pues es que estamos compitiendo, pues, sana la competencia, ¿no? Entonces, está bien.
Oye,
Pero hemos
Zacatecas
hecho,
está re bonito, ¿no?
sí, cuando vienes por 2 semanas. O sea, la ciudad es muy bonita, claro, puedes caminar por ella y todo, pero después de un año de estar aquí y haber conocido todo, pues ya. Pero sí, está bien, es tranquilo. El problema de los narcos, pues es a nivel nacional, pero bueno, aquí
Pues,
también hay muchos problemas de eso.
Sí.
Pues sí.
Bueno, ¿quieren que retomemos? No sé qué dicen los jefes. Estefan, Alan.
Sí se ve entonces mi presentación, ¿verdad?
sí, sí.
Sí,
Súper
sí,
bien.
sí.
Ni te pregunté, pero ¿te puedo grabar?
Sí, claro.
Gracias. Tenemos otro zacatecano por aquí. Aquí anda Leo.
¿Quién es?
Leo, Leonardo, pero él es químico. Creo que por eso no lo ubicas. Pero él también es de Zacatecas.
Ah, ok. Entonces estudió en la UAS.
Sí, hola.
¿Dónde está Leo?
De hecho, yo estudié en la facultad bueno, ahí en el campus en el siglo XXI, pero yo soy
Química.
ingeniero químico. Ujú.
Ah, ok.
No sé si conozcas esta María Isabel Pérez Martínez.
Sí, claro, claro.
Ah, pues ella fue mi asesora de la licenciatura.
Ah, sí.
Sí,
Ah, pero entonces, bueno, ¿qué estás haciendo por ahí? Entonces tú, ¿en el instituto estás haciendo alguna maestría o algo?
estoy en el doctorado ahorita.
Ah, en el doctorado. Excelente.
Pues no sé. Alan. Alan. Estefan. Are you
¿Qué
there?
pasa?
Ah, no, pues sí, ya empezábamos, pero claramente
Pues,
no.
pues no, pues, ¿quién es Chair?
Yo, pero
Pues,
pues no, pero pues los jefes no están.
a ver, cuando hay Chair y manda el Chair, no los jefes.
Tú eres la jefa hoy.
Ok, entonces comenzamos, por favor, Alejandro.
Ok.
Tu charla es cortita, entonces te aviso cuando te falten 2 minutos, ¿sale?
Espero no pasarme, pero sí, por favor.
Gracias.
Okay. Yesterday, Professor Jean-Luc said that I agree with him that there is a big gap between observations, models, and physics and microphysics. So I think it's hard to have a holistic view of all the advances in physics and implement them in our models. And therefore, my talk is just to call in a very short talk your attention to some relatively new aspects of neutrinos implemented in the calculation of supernova energy loss rates. So results of this work has been published already in these 2 papers that you write. And the main goal is to explore the new interactions and understand the properties of neutrinos, such as the anomalous magnetic moment and the dipole moment that lead to important astrophysical and cosmological effects as they can carry more or less energy from the background. Thus, this is done within the context of the UVL model of elementary particles that, and I am not going to discuss in details. And of course, we assess the effects of these moments on the stellar energy loss rates of core collapsed massive stars, some very common physical processes of perennial electron positrons, mainly at the electroweak era of the universe. Well, the main motivation is very extensive. So I am going to address mainly the importance of the electromagnetic interactions of neutrinos in cosmology and astrophysics. Many extensions of the standard model, as the one I am using here, the U1BL model, account already for neutrino mass oscillations, but also predict non-trivial electromagnetic properties as the ones I have mentioned. Those new properties allow direct electromagnetic interactions of neutrinos with electromagnetic fields and other particles. This elementary particle model, in this model, neutrinos are not produced in purely left-handed states, but also right-handed states, increasing the thermal excited degrees of freedom in the early universe. This is really important because if we calculate, for instance, the temperature of the couple of neutrinos as a function of the degrees of freedom, we have a very interesting predictions, which means that the neutrino temperature has to be around 1.95 kelvins. Meanwhile, the cosmic background radiation temperature is 2.7, and this has to be tested. So
2 minutes.
the temperature, sorry?
2 minutes.
Already?
If you want to take another 2 minutes, it's okay. Don't worry.
Okay. And the other one, very impressive work done with neutrinos is the confirmation that this baryonic oscillation, the power spectrum of the density fluctuations, are the neutrinos are mainly reasons for this. So we can use neutrinos as with some important application of high energy astrophysics, like those that I listed here. And the table, you can see the magnetic moment associated for the neutrinos. Those are the most significant ones. And of course, well, to study this, I use this for main mechanism of the production of neutrinos, the ones to the upper left. And the first one is the most important mechanism of neutrino production. So I present here the Feynman diagrams, and we follow the common procedure, which is to calculate the square amplitude of the transition, then the total cross-section, and finally the stellar energy loss rate. I don't want to get you bored with calculations, but we can do it this in a very beautiful way because it's analytical way, so there is not approximations in here. So we can calculate the emissivity due to the parameters of the model, but also of these two electromagnetic new moments for neutrinos. And finally, we can compare with the standard model. As you can see here in this first equation, there is the emissivity of the new model compared with the emissivity of the standard model in different regions of interest. You can see here the temperature, the density in the medium, and the different cases that we consider not relativistic and not degenerate, mildly degenerate or relativistic, and all the combinations. Well, some very interesting and important results, I think, are these plots. If you, for instance, follow the variation of non-zero moments, you will see that there is an important contribution coming from the moments, and also with the new mixing angle, which is represented by theta BL. So this is a comparison of the percentage importance with the difference of the emissivity in these two models. Well, okay. Okay, these are my conclusions. Electromagnetic dipolar moments have important effects on the emissivity of supernova. It's in fact 20% higher than predicted by the standard models. The parameters of the DL model have significant effects on the supernova emissivity. Unfortunately, there are several other extensions of the standard model that can produce the same effects, well, more or less the same effects. And probably the most important one is the following, that our analytical expression for the stellar energy loss rates show a better results than just using wrongly the same equation and replacing the new couples, assuming that the universal equation is useful for these calculations. But this equation has to be changed and appropriated for the situations. The future work is very, very promising because our calculations allow us to explore some other consequences in different areas of cosmology and astrophysics. For instance, we could like to apply this for the sun, for different types of stars, different types of supernova, probably in the connection of supernova with gamma ray bursts. And of course, we can perform some extensions of the effects of the primordial density fluctuations and to explore the different other mechanisms of production of neutrinos. Thank you.
Thank you, Alejandro. I don't see questions in the chat, but I have a question. And it's because I know that you work with David, and I am interested what you plan to do with Messier.
Well, I think the idea is not new. Is to explore the neighbor local universe, trying to find tidal effects of interaction of galaxies and try to reproduce roughly the evolution of the local universe. And of course, we need to have a telescope able to do this at these scales. But I mean, it's just for the moment it's just a plan.
Okay.
The telescope is not ready, so it's a project for a long time period.
Okay, thank you. Jean-Luc has a question, please.
Yes, this is a very naive question because I don't know this field very well. Could this have an impact on the masses, expected masses of neutron stars, the maximum mass of neutron stars, something like that, or not at all?
I think that is possible, mainly if we relate this mainly with temperature. I haven't done the analysis yet of that, but I am quite sure that the mass can be some way included in the temperature and the generacy. At the moment, I am not quite sure about this. I need to think about it.
Okay, thank you.
Okay, and last one from Enrique, please.
Hi, yes. Are there any changes on the expected neutrino oscillations or something? You mentioned also that that this has implications for the sun, but I think those or the amount of neutrinos that you see from the sun are what you would expect, not 20% above or below. But if you had different oscillations, perhaps you could mess around with that a little bit.
Well, as I said, there are plenty of things to do. That is one of the main goals in the near future. And also to extend this to some other stars, for instance, white dwarfs, red giants, because from those stars comes the best bounce to the values of these electromagnetic moments. So that is the next step, yes.
Thank you very much, Alejandro. And we continue with the program. Please, Gibran, are you there?
Yeah.
Could you share your screen, please? Alejandro, please stop share your screen.
Yes, sorry.
Thank you. May I record your talk, Gibran? It's okay? Thank you.
Yeah, it's okay. One second. Okay, I'm ready. Okay. I think it's this one. Yeah, is everything okay?
Sí, te aviso cuando te queden, ¿qué son? 3 minutos, ¿sale?
Okay.
Dale.
So hello everyone, my name is Gibran Morales. I am a student at Instituto de Astronomía UNAM and my advisor is Nisim Freiha. Today I'm going to talk about neutrino propagation in winds around the central engine of short gamma ray bursts. Short gamma ray bursts are a subdivision of gamma ray bursts which last less than, typically last less than 2 seconds. And progenitors of these sources are the merger of 2 compact objects, either in black hole neutron star or neutron star configuration. In the first case, the associated magnetic field to this progenitor is only the magnetic field associated to the isolated neutron star, which typically is 10 to the 12 Gauss. But in the second case, several studies have shown that the magnetic field could be amplified up to 10 to the 16 Gauss. So during the formation of these short gamma ray bursts, several winds are produced, and these are produced these are produced to explain a cooling mechanism for the post-burst debris. There are 2 main proposed mechanisms. The first one is the neutrino-dominated accretion flows, which neutrinos of around 50 megaelectron volts are produced by burst annihilation within the accretion disks, increasing the neutrino density gradient, which drags and hits the surrounding baryonic medium into the so-called neutrino-driven winds. The disadvantage of the previous mechanism is that it results in an extremely inefficient process because it requires a large neutrino luminosity over short time scales. Those other mechanisms of energy extraction through magnetohydrodynamic processes have been proposed. In these magnetic processes, the toroidal magnetic field are forced to reconnect quickly and then twisted due to the differential rotation of the disk, hitting the surrounding medium and ejecting the wind outflow. In this case, a very intense magnetic field is needed to do that. So here at this point, we ask ourselves, do the winds really affect the neutrino propagation? Because every work performed until now has considered that neutrinos have a small cross-section and they are released in an isotropical way. And for that, the oscillation probabilities could be approximated to the vacuum case. So let's see in this work if this will work. we found that actually these winds affect the neutrino propagation, and we demonstrate that on this typical energy range, the mega electron volt range, neutrinos produced at these sources, they will oscillate resonantly. And that's because the neutrino potential, which is the physical parameter we require in order to compute the probabilities, is dependent on the medium density. And as I said before, these wind profiles were unknown until now, because several simulations have been shown that the winds, it is really, how can I say it? Like the density profiles of the winds are unknown until now, because several simulations have been performed to describe these density profiles. With these density profiles, we can obtain the neutrino potential associated with these profiles, mainly by these two mechanisms that I explained in the slide before. And these results were summarized by Murguía-Bertier in 2007, where she showed these two density profiles associated with these two mechanisms. Once we have these density profiles, we can compute and obtain the neutrino probabilities in all the cases. We know that there are 3 neutrino flavors, so there, we will expect 9 allowed transitions, which 6 of them are independent. In the case of the vacuum, the probability is only function of the neutrino energy, the oscillation length, the mixing angle, and the squared mass differences. But in the matter, we need to add an additional contribution associated with the density of the medium. So for that reason, it is important to know that the density profiles that are associated with this mechanism. So in this slide, we present the survival probability of the neutrino electronic. We present the survival probability of the electronic neutrino, and as we can see, there are resonant pattern effects in both cases. In comparison, if we consider that neutrinos are released isotropically, there will not be any angular distributions, and the plots would be simply vertical stripes. So it is worth mentioning that terrestrial detectors do not measure neutrino probabilities, but neutrino ratios instead, which are the amount of neutrinos of each flavor that they can detect. For that reason, once we know the probabilities, we can estimate these ratios with the conditions in both cases. So in this slide, we show the ratios for both cases, the magnetically driven winds and the neutrino driven winds for a neutrino with energy of 15 mega electron volts. In the continuous lines are shown the percentage of neutrinos expected. The red line is for electronic neutrinos, the purple is for muon neutrinos, and the blue one is for tau neutrinos. In comparison, we also show in dashed lines the expected neutrinos in the vacuum for electronic muon and tau neutrinos as well. So
3 minutes.
3 minutes? Okay. And as we can see, they differ from the vacuum case in both cases. They are not like similar in the vacuum case, but the most predominant effect is in the first one, the magnetically driven ones, where we have an additional contribution due to the medium. For example, if we are able to see an off-axis GRB with an angle of view of 10 degrees, and we, in our detectors, we detect a neutrino ratio of 0.38 in electronic neutrino, 0.31 in muon neutrino, and 0.31 in tau neutrino, that will indicate that neutrinos were propagating within a neutrino-driven wind scenario. This could lead us to indirectly determine which kind of progenitor would be associated with the source that produces that this kind of neutrinos. And yeah, that's all. Let's go to the conclusions. We derive the effective potential for neutrinos crossing the winds. With this effective neutrino potential, we can compute the resulting oscillation properties and compare them with the vacuum case in order to know if there will be any effect due to the winds. In particular, we found a stronger angular dependence on the expected neutrino ratios, and we can conclude that the joint analysis of this observable together with the short gamma reverse ejected jet angle could lead to a compelling mechanism to discriminate between the involved merger according to the expected neutrino ratios. And yeah, that's all.
Thank you, Gibran. If you have questions, Fabio. Please, Fabio.
Yeah, so what about the intergalactic medium? Is completely negligible or can also contribute to the neutrino oscillations?
Yeah, the intergalactic medium could be approximated as the vacuum, since the neutrino cross-section is really small and they cannot affect the oscillations. So in order to compute the final probabilities, we need to do something called slab approximation, which requires the expected neutrino ratio that I presented in this work, and just we need to add the oscillations in the vacuum since the source to the Earth.
Which is the length scale for the oscillation of neutrinos in a vacuum? I mean, how long would you take? How long does it take for a neutrino to begin oscillating in parsecs or in megaparsecs?
Yeah, the oscillation, the typical oscillation length in this case is something between 10 to the 7 or 10 to the 9 centimeters. And this is dependent on the neutrino parameters that you choose to fit the neutrino oscillation length. So I didn't show in this presentation, but I actually in my work in progress, I demonstrate that the oscillation length is typically smaller than the length scale of the winds. So they in fact will oscillate resonantly.
Okay, thank you.
More questions? Because I have one. What's the accuracy or the precision that you could, or the person could measure this rate? Because I remember that was very similar, 0.32 and 0.36. It's not very similar to discriminate? Or,
Yeah, it could have some problems because they are like really close. But you need to know that in order to have like a better statistics, you need several detections. And for example, if you have like let's say something like 100 neutrinos, and you can like determine how many neutrinos of each flavor you are detecting, you will have a very more accuracy detection rate to this case. We expect that future neutrino detectors are sensitive enough to detect these neutrinos in this order of magnitude. And in a previous work, I I showed that, for example, the hyperchemical detector could have it, how can I say it? The hyperchemical detector would have detect neutrinos from the event in with the gravitational wave in 1708-17, but if the source were more energetic, because this source was close enough to the Earth, but it was weak in energy.
Okay, thank you, Gibran. William sent you, or sent for all of here, a link.
Yeah, it's a reference to a paper about neutrino oscillations in gamma reverse and energy deposition to avoid baryon contamination.
Thank you, William. Then here we stop with the talks. That was the last one. I want to thank to all the speakers of today. And thank you very much for your presentation. And we can continue with the discussion. We skip the coffee break. And we can start with the discussion. If anyone want to share some point of view or want to ask something, this is the moment.
If nobody has a question, with Arnaud, we can come back on the data policy on SVOM if you want. Arnaud? Arnaud?
Oui. Excuse-moi, comme j'avais pris un coup de téléphone avec Tatiana,